Right, when you look at this first group, if you can identify, rather than distribute the first factor through, add them up, and then look to refactor, if you can identify that this is two groups of factors separated by a minus, and they have a common binomial factor, right? They each have a 3x minus 1. So if we take out that 3x minus 1, the remaining pieces have to have the same form as the original, one group minus another group. And if you look and divide out the 3x minus 1, that leaves a 2x in our first group and a negative 3 in our second group, and that's all you have to do. There's no further factors. Those are going to be the two binomial factors of your expression. Like I said, if you distributed through, combined your like terms, and then factored, you'd still wind up with this, but if you can see this form, it's going to be much more efficient. All right, the second example is one where you can either use trial and error, or you can rewrite the middle term. Again, my preference is usually going to be rewrite the middle term, just because it will always lead you to the answer the first time without having to waste any checking. Okay, so if I take my leading coefficient times my constant, I get a negative 40. Are there two factors of negative 40 whose sum is this middle term's coefficient, positive 18? Yeah, it's a plus 20 and a minus 2, right? So if I rewrite my middle term as negative 2x plus 20x, now it doesn't matter which term goes first. If I have a positive and a negative, I'll probably put my positive second, because then I don't have to factor a negative out when I factor by grouping, and it just makes it a little bit easier. So I'm going to drop down the first and last terms and factor by grouping. Okay, so if I look at the first pair of terms, what common factor can I remove? 2x, and that leaves 4x minus 1. What common factor can I remove from the second pair? 5, leaving a 4x minus 1. If I've done this right, and if it can be factored, I should have a common binomial factor, which I do. So that gives me 4x minus 1. And then when I remove that, again, what I'm left with are the two terms, 2x and a plus 5. So that becomes my second factor. All right. The last example, again, what should I be doing first with this problem? Remove that common factor of 4. That leaves an x squared minus 9. And again, this makes it smaller numbers to work with and not having to worry about to factor your sum and difference factors. So I do see that I have a special factor form here, the difference of two squares. So I'm going to factor that into the sum and difference of the bases that are being squared to give each of these. So the first term is the base x squared. The second term is the base 3 squared. So if I take x and 3 as my terms, take the sum and difference of those, I get my factors. Okay. In looking at this, what you should be able to recognize first, check to see, can you remove any common factors? No. But what do you notice about each of these terms? They're both perfect cubes. Okay, so if we look at what bases are being cubed for each of these, we see that we have the base 5x being cubed and the base positive 3 being cubed. Okay, so the sum and difference of cubes has a specific factor pattern. It's a binomial times a trinomial. Again, this is not the binomial expansion for a binomial cube, and it's a separate factoring rule. Okay, so the sum of cubes factors into a binomial times a trinomial. The binomial is just the sum of the two bases being cubed. So a 5x and a plus 3 is the first factor. Okay, now the second factor is a trinomial, meaning 3 terms. The first term is the first base that we have here squared. So we're going to square the 5 and square the x. That's our first term. The last term of our trinomial is the second base squared. So we square the 3. That gives us a plus 9. And so finally we have just this middle term left. The middle term can be found by taking the product of these two bases and changing the sign. Okay, so 5x times 3 is 15x. Change the sign, we get minus 15x. And that gives us our set of factors. All right, the second example is a case where you can either use trial and error or you can rewrite the middle term. Okay, so normally what I'll do is rewrite the middle term for these. So if you look at your leading coefficient times your constant, 6 times a positive 5 is a plus 30. Okay, what we want to do is find, are there any two factors of positive 30 whose sum is the middle term's coefficient, negative 17? So what two numbers can multiply to give you positive 30 and add together to give you negative 17? Negative 15 and negative 2, right? So if we rewrite that middle term as the sum of those, it doesn't matter which term goes first. Drop our first and last term straight down and factor by grouping. What we can see is, what common factor can we remove from the first pair of terms? 3x, leaving a 2x and a minus 5. What about the second pair of terms? Again, there's no common factors between the terms themselves. You always take out the sign, so in this case the minus. And if there are no common factors, just write a 1. So you want to see the 1. If you don't write the 1, it's very likely that you'll make a mistake when you simplify. But if we take out a factor of negative 1 from each of these terms, we're going to be left with just their opposites. So the opposite of negative 2x is a positive 2x, and when we factor out a negative 1, we get the opposite of 5, which is negative 5. Now, if you've done this right and the whole expression can be factored, you should have a pair of common binomial factors. So we have the 2x minus 5 is a common factor between both of those groups, so that comes out. And then the remaining factors of 3x and minus 1 are going to form the terms of your other binomial factor. And so you get this as your factored form. All right, the final example, again, the first step is to remove any common factors that you can. So what common factors can you remove from these two? Remove a 4. When you remove a 4, you're left with x squared and a plus 9. And now you have this binomial, or this sum of squares. Is the sum of squares one of our factoring patterns? We have difference of squares. We have sum and difference of cubes, but do we have a sum of squares? No. A sum of squares is said to be irreducible over the reals. Okay, so a squared plus b squared has no specific factors. So you can't factor x squared plus 9 into x plus 3 quantity squared, right? Remember, the expansion rule for that would involve a middle term of plus 6x. Okay, so x squared plus 9 would just stay as it is. It's irreducible over the real number system. Okay, and so this would be as far as you could go on your factors there. All right.